Tuesday after break, whatever date that is. The lab, we go until Thursday. Thursday after break. There will be another lab coming up, that's appropriate and posted probably this afternoon, which is obviously next step. We got to make an observer for the system. Same system, same everything, so virtually the same measurements and all. So it'll be, once you get the first one done, the second one, well, it's a bit more programming in it because you have to make the observer, but it's not that terribly hard. Right? Okay. Questions on any of that? That makes sense? Okay. Yeah, sorry I did the schedule. I forgot completely. In fact, I had even had the wrong dates for tourist robotics. So the schedule got completely messed up in that regard. So.
Is it possible to do the lab tomorrow instead of Thursday, or is it going to be available for that time?
Yeah, we could probably do that.
Okay.
Yeah. I'll talk to the TA. I need to get you guys access to the lab too.
Okay.
I think only need UID, your name, and have all that. So.
Okay.
Yeah, what we'll do is, yeah, if you're familiar with the lab and familiar with the equipment, go ahead and use it. You can use the launcher. For those that haven't used it, certainly Thursday, let's get in there and you'll have a lesson on how to use the stuff. It's really pretty simple. But if you've used the Quantum stuff, yeah, go ahead and get in there. And I'll see what time it is available.
Okay.
Yeah.
If you got us access last semester, will we still have
It's
it?
gone. It goes every semester.
Okay.
It goes quite quickly. Or we might check, maybe they forgot to wipe it, you know. But usually all the plastic cones get wiped out. Okay, anything else? One thing on the lab, if you've read it, not yet, is you kind of ask for step input. So let's talk a little bit. We're going to have, after break, talk a little bit about inputs to the system, but at least a simple input you can do to the system. Because so far we've talked about regulators. So we have our system, a plan, out of which we get all of our states. We're assuming we get to all those states. In the first lab, we're going to feed those into feedback gains that create U. That's the first lab. Second lab is the plan. All I have is the output Y. It goes into, we'll call it a controller observer, and it creates U. Okay? Today we'll talk about structure that. I'll show you a map so you can get these pretty easily. There's no input here, but we can put in an input. Okay, look at this. Let's put in an input. And I'll assume that I have lots of pluses. So I put the minus things down here, makes no difference. Have some input. Well, let's say we want the desired position. And let's say that's state one. All right, so state one is, this position. Right? But what we're coming out of here is what? What's U? What was U? Well, this unit volts, I'm going to get back to dimensions here too. But how do we find it? It's what K times states, right? Correct? So I have all these states, let's say that, system is second order, 2. So really this is kind of gain times x1 is position, gain times x2 is velocity. What do I want here? Anybody suggest what we might want to put there? Maybe we should make this minus here. Minus u. What will we put there? Which K? K1. So this, yeah, this is fine, because now what goes in here, call this u prime, is what? It's K1 times x desired, so this x1 desired, minus K1 x1 minus K2 x2 and so forth. So what I have here is x1 desired minus x, which is what? The position error, which is perfectly fine. What have we essentially done mathematically in this thing? Regulator tries to do what? Always tries to drive the system to the origin, correct? Well, what have I just done? Change where my origin is. That's all I've done. So instead of driving it to 0, I'm driving it to x1. That's the easiest sort of way you can do a input to it. Okay? Does that make sense to you? That's the type of thing you can do for the lab. Now, what if I just simply put step input here? Didn't scale or anything. Is that okay for determining what my response is? Because what have you done here with this lab? We've specified a desired closed loop roots. Okay? And I want to see if my system actually goes to those desired closed loop roots in an experiment. Would this do it? Why? Or wouldn't it? How are you going to determine what the roots are? Give it some kind of response.
Response characteristics.
Well, give it some sort of, it could be a step, it could be impulse, it could be something. And I want to determine what those roots are. How do I do that? Maybe give it a step input. How do I determine what the roots are to the step input? Overshoot, time to peak, all those things. Do those things matter what the magnitude of the step is in a linear system? No. Percent overshoot, time to peak, independent of the magnitude for a truly linear system. Right? What you need to make sure, however, is that our system stays linear. Right? What might make it? It's a physical system. Physical systems are not linear. What would be non-linear about our system potentially here?
Static friction.
Friction, okay.
Gravity.
What's that?
Gravity.
Yeah, it's balanced. Gravity, we've zeroed that back because it's horizontal. But that potentially could be. Well, let's think about practicalities of a motor. In amplifiers.
So they have limits?
Yeah, they have limits. Amplifiers can saturate. Motors have basically max velocities they can drive, things like this. So you want to make sure you stay below those limits. Okay? So a really big input, you might get some very different response than from small input, just because I get saturations and other problems. Too small an input, then maybe the coulombic friction starts mattering. Because it's not strong enough to kind of keep it out of coulombic friction. so there's some practical problems you need to kind of swap. Okay? So for the lab, Aggie's going to step to them after, did I hit those routes that I was after? Okay. Does that make sense to everybody? Questions on that? Okay, another one, Brian, it's a good one. Go back to our nice simple regulator here. Our system, I think it's actually in current mode, so it says voltage, we say it's voltage, this is voltage. What are the dimensions of the states? Well, position, rotary system, position might be what? Might be radians, all right, so this could be theta, omega, possibly radians, and maybe radians per second. Right. How do I measure position?
Potentiometer, tachometer.
Potentiometer, encoder. Now, the quasi system has a encoder in it. It's done all the scaling for you, so you don't have to worry too much. Well, let's say I've had a potentiometer. Potentiometer, you guys have used these in electronics class and other classes. The position output of a potentiometer is what? Absolute is like a voltage. Voltage across there gives us some angle. So input angle, output voltage by some scaling. So potentiometer might have some number associated with it. It could be, in fact, one we have for one of the lab systems, 1.69 volts per radian. Okay. I'm with 1 radian, I'll get 1.69 volts. All right. How about a tachometer? So we use measuring angular velocity. What are those usually rated? In fact, often the silent will tell you what the scale is on it. So it's usually so many volts per RPM. You know, tachometer. So many 0.1 volts per 1,000 RPM. Actual, let's say radian. Let's keep it radian per second. Keep it simple. There's so many volts per radian per second. Right? When I calculate the K's using Archimedes relationship or whatever, do they have dimensions? Yeah, have to. In fact, what would it be? I simply have my model, output is theta and omega, there's radians per second, there's voltage. K for the position must be in what units? Volts per radian. Okay? So K1, that'd be volts per radian. And K2, that'd be in like volts per radian per second. Right? But my transducers that are actually measuring these things are giving me what? Voltage. But my gains are expected to see radians and radians per second. What do I have to do? You do some conversions here. So let's look at this guy. So and let's give it some numbers. Say we want 2 here and 3 there, just to make some numbers. So this is 2 volts per radian. This would be 3 volts per radian per second. Okay. We're actually measuring. Here's our transducers. Actually, let's do this. Here's the potentiometer. And tachometer. This would be X2, X1. This is what I physically measure, this is what's going into our controller. Some voltage. Let's call this K1 prime, K2 prime. This whole thing must be equal to what?
Units wise?
Okay, I calculated from the axis formula. So this must be K, let's call it from acronyms. And this must be K2, SE for acronyms. But this is what I actually am measured, this signal and that signal. So in the computer, if I have, or my controller, if I have a clock tachometer here, I don't enter K1 from acronyms, K2 from acronyms, I enter what? These guys. All right, so I need to account for gains in the transducers. That makes sense. In fact, these units are what? What are the dimensions for K1 prime and K2 prime? Radians to volts. This is going to be volts. So this is what unit? Volts per volt. Yeah. This is also volts per volt. Does that make sense to you? Do? Right. Now, computer setup and the quantum system setup that I did for this, it has these gains built in. But it does the calculation for you. I'm pretty sure the way the software does. Does that all make sense to you? Again, you can't just blindly say, oh, I put in this number I found from the computer because my transducer's not giving me what I expect. Yeah.
So the K1 prime and K2 prime are going to have to get us back to volts.
Yeah, this is the K pot, K attack. So K1 prime will be what? K1 prime times K pot must be equal to K1 from the acronyms. All right. K2 prime, K attack must be equal to K2 that I found from acronyms. So I need to adjust my gains by the gain of the potentiometer and tachometer, or whatever other transducers I have. All right, does that make sense? So this is what I actually put in. And I can do that with an op-amp. I mean, op-amp with the right gain. Right? That all makes sense to everybody? All right. I'm going to show you